Okay. All right, let's get started. I'm sorry for not having your grades back. I have no excuse except that I'm behind. So please bear with me. Wanted to start talking today about clustering. Principal components is one good off-the-shelf way of visualizing multivariate data, in particular multivariate numeric data. As a reminder, there is a principal component-like method for doing something similar with categorical variables. And I am going to come back to that and show you how to do that with software and some real data. But imagine you have a bunch of columns in your data set, and they're each categories: gender and race and education level and stuff like that. What kinds of associations and joint relationships are there in the data? But where we're going to go right now is a slightly different kind of investigation called cluster analysis or clustering. The idea is we're going to have our N by P matrix of numbers. So we're again talking about numeric variables for now. So we have individuals in the rows and we have variables in the columns. And the clustering idea is to find groupings in one or the other. And we can go either direction. And depending on the circumstances, you may want to go cluster the individuals, or you may want to cluster the variables, or in some cases both. But for whichever collection of entities we're going to cluster, whether it's the individuals, the rows, or the variables, the columns, we apply a generic algorithm. So in clustering, we group together either the individuals or variables. Individuals are in the rows, variables are in the columns. Grouping together, what we mean conceptually is finding, suppose we talk about the rows, the individuals, the people in our data set. A cluster would be a group of those people who are similar to each other, more similar to each other than they are to everybody else. So imagine in a simple case that we could group our N individuals into two groups very clearly. There's one group that has values that tend to be in a certain neighborhood, and there's this other group that look very different. Cluster analysis should be able to discover that type of grouping. And the way it does it is by asking how similar are two individuals to each other. If we're going to group into these clusters, we have to be able to say how close are any two individuals or any two variables. So suppose we cluster the individuals. The rows. I'm going to find in my database of credit card transactions, I'm going to find groups of customers or clients, rows in my data set who are similar in some way. Okay, so if we cluster individuals, then everything is going to be driven by a distance matrix is what it's called. This is what we're going to work with. We've been working with covariance matrices, doing inference and principal component decomposition. For the purposes of grouping, we switch attention to a distance matrix. So dii is equal to 0, and dij is equal to some distance between individual I and individual j. If you have two vectors of numbers, you have two rows in your data set with numbers in them. What's the distance between those two vectors of numbers? We know some ways to compute that right off the bat, like a Euclidean distance. That's just a distance between two vectors. So we could define distance in the bottom right as the square root of the sum of the squared differences component-wise. But there are a whole bunch of distance definitions that you can choose from. And there's no one right one for every circumstance. So part of what we'll see in our notes is this is the general idea. This is the beginning of the idea. We're going to start by the investigation of a distance matrix. We have to define what we mean by distance. And there's a table full of possibilities. Some of them are more appropriate to different applications than others. Once we decide how to define distance, then we can consider what algorithms specifically are we going to use to discover these distances or these clusters. The problem is not well posed enough to have an analytical solution at this point. It's not like the answer to the problem is go get the eigenvectors or something. This is a more subjective exercise, and there's a variety of methods or algorithms that we could use. I'm going to show you two of the most prominent ones called hierarchical clustering and k-means clustering. And so what we'll see is that working from the distance matrix, we can discover clusters using two main algorithms, hierarchical clustering and k-means clustering. There are other model-based methods, and I'll mention those if we have time, like assume a probability model for your data and discover groupings within models, mixtures of models. And I can explain the hierarchical and k-means clustering very quickly on a whiteboard, and then I'll show you the details in the notes, but the concept is very simple for both. With hierarchical clustering, step one is to join the two individuals who, out of all pairs, are closest. So you look at the distance matrix and you go find the smallest number, except for the diagonals, because the diagonals all equal 0. You go find which row and column combination corresponds to the smallest distance. Who's closest right now? And you call that a cluster. Call it cluster 1. Cluster 1 now contains two individuals. And you can think about it, at the very beginning of this, you can think about it like we're beginning the algorithm by assigning every single individual to their own cluster. We haven't done any grouping at this point. And we're going to iterate to group together, group together, group together until we've grouped everybody together. So we're going to have like a tree that goes from no grouping to we've grouped everybody, and you'll be able to see how they go together by investigation of the tree. That'll tell us this grouping of individuals was very close to each other, very similar. We'll call that an overall cluster. And here's another one. So the algorithm, you begin by every individual is their own cluster. The algorithm says, step one, go find the two individuals who are closest with the smallest distance and put them together into a new cluster. So now there's n minus 1 clusters in the situation. There's all the remaining individuals, and then the two who were closest have been joined into just one. Step two is then recompute the distances, because now that we have a cluster containing more than one individual, we have to rethink what do we mean by a distance. If we're asking, for example, what's the distance between individual 10 and these two individuals, individual 1 and 4, who were grouped together in step 1. Euclidean distance is one example. If you just have two vectors, what's the distance? But what if you have maybe a group of vectors and another group of vectors? What do you mean by distance between clusters? So doing that step, we're going to have to consider another place that you make a decision as to what type of clustering you do, and that's called the linkage definition. There's different ways of defining what we mean by the distance between a group and another group. There's three main choices that are used typically in practice. I'll show you them, and in your homework you'll actually get practice with trying the different types of linkage. So you recompute the distances. Now you have an n by n minus 1 by n minus 1 distance matrix, and you again find the smallest entry. So now you join the two arbitrary clusters now. I'll say join the two closest clusters. And so at the end of that stage, another pair, most likely, has been put together into a cluster of two. And you repeat until one giant cluster. We don't want to group everybody into one group. We want to discover meaningful subgroups. The hierarchical algorithm starts with no grouping and goes all the way to complete grouping, and it's by inspection of the output that you decide where the subgroups are that you think are real and worth investigating further. So hierarchical clustering is this iterative algorithm. K-means clustering, I think it'll be more instructive if I show an example before moving on to K-means. So let's look at an example of what hierarchical clustering does. I'll go to old standby Hall of Fame data. the data. Let's come down here and do cluster analysis. So here is hierarchical clustering. The magic function for doing hierarchical clustering is hclust. So let's look at the help file for hclust real quick. Oh, before I forget, okay. This topic of cluster analysis and the preceding topic of principal components, these are exploratory techniques for multivariate data. They are, in some circles, called unsupervised learning techniques, in the sense that a supervised learning problem would be we have these data, the N by P data for a bunch of individuals, but we also have for each individual some class characteristic like cancer or not, or this is a spam, this is a normal email, or even a numeric value like prostate-specific antigen concentration or something. When there's a overall goal of modeling and predicting the value of some known quantity, that type of data is called training data, and it's the type of data that's tackled by supervised learning. Supervised learning will have 4 weeks on coming up soon, and that's like predictive modeling. So use regression to predict a numeric variable, or use logistic regression to predict a binary variable, or multinomial regression or lasso. All those things are supervised learning. When we get to that material, I'm going to be pointing you to this book as a supplemental resource. And if you Google the book and come to this of the first author's website, Gareth James, he has a PDF that you can download for free. And it's R throughout. So things like lasso, random forest, support vector machines, if you're interested in learning more about those types of things, there's some practice starter material in this book. Because I don't have time in this class to go to the really sophisticated machine learning techniques. So I wanted to show you in this book, chapter 10, the last chapter of the book. The whole book is on supervised learning, basically, predictive modeling. And their final chapter is called Unsupervised Learning. So unsupervised learning is what we're doing right now. It's principal components and cluster analysis. So they will have kind of an intuitive explanation of principal components and an illustration with some real data. And similarly for clustering. So I recommend you read that chapter of the Introduction to Statistical Learning book. So I wanted to look at the help file for hclust, so we can put it into action and see what it does. hclust hierarchical cluster analysis on a set of dissimilarities and methods for analyzing it. It says a set of dissimilarities, and what that means to us is a distance matrix. Clustering is all about distances, and the hclust function takes as its main argument a matrix of distances. So over here in R, before I call hclust, I'm going to save the output of hclust with a distance matrix, and then I'll fill in some details. So I need a distance matrix, and there are various ways to compute one. For a Euclidean distance matrix, there's a built-in function. We have our N by P matrix of numbers, and if I just say dist x, I think it's going to give me back the 6 by 6 matrix of distances, or maybe not. No, it did 1016 by 1016. So if I do dist transpose x, there's 6 by 6. So we can actually see that one. That's a distance matrix. The diagonals are 0, so they're not even shown. And then the off diagonals are all Euclidean distances between the variables. For example, square root x hits minus RBIs, square those, and then add them up. So those are all Euclidean distances. And again, I'll show you in the notes, there's other ways to define distance. It doesn't have to be Euclidean distance. For illustration purposes, so that we can actually see clustering in action, let's just do Euclidean distances. So I'm going to say capital D is dist, and whether or not we say the dist of x or dist of the transpose of x, that determines what are we going to be grouping into groups. Do we want to group the players into groups, or do we want to group the 6 variables into groups? We could go either way. I'm going to try to just do grouping the individuals. So now capital D is a big matrix, 1016 by 1016. Let's see if it works for us. So that's what I'm going to pass into hclust. Let's go back to the help file and see what else we need to provide. The other main argument to hclust is this method argument. And this is what I called the linkage method. This is our definition of what we mean by a distance between 2 groups of individuals. We'll talk about this in the notes when we get to it, but there's 3 main choices. There's complete linkage, single, and average. The default, according to the help file here, is what's called complete linkage. So for simplicity, let's just let the default be what we use, in which case I can just say hclust, my distances. So if we do this, let's see what happens. HC.
Which distance parameter we use, will they all produce similar results?
If you use different distance definitions, will it produce different results?
Yeah.
Sometimes. Yeah, so one of the challenges with cluster analysis for sure is that it requires subjective input. There's a bunch of different ways you can do clustering. So you could end up with, well, here's 10 different possible ways of looking at our data. And ultimately, you have to make some common sense, best guess decisions about which one to use. What you don't want to do when you're doing exploratory stuff is to try every possible way of looking at the data and pick the one that looks most interesting or that looks like it supports your research hypothesis most. As much as possible, make a few clustering pictures and pick one just using common sense and be reasonable, be conservative, pick one. And try to resist the urge to fish around for all the millions of possible ways to cluster it. So what you would typically do is, at the beginning, okay, I have data that are of the type, they're financial, they're dollars and cents. So it makes sense to me to treat them just like a real number. I'll use Euclidean distance. If you were studying traffic times of taxi cabs in New York City, and your distances have to do with city blocks, and it's not like a straight line distance, then there's a different type of distance that's like city block type distance. So ideally, you make as much decisions as possible at the beginning. Go make some targeted pictures and walk away with 1 or 2. Yeah. All right, well, let me just show you one picture. When you do hierarchical clustering, if you ask for a plot of the result, this is the kind of picture that you get. This is the tree-based kind of representation of going from every individual is its own cluster to everybody's been grouped into one giant cluster. The joining points, as you go from bottom to top, you're watching going from more clusters to fewer. And the joining points, the little horizontal connected line segments, represent groupings. So if there's a grouping, two lines come up and they join, that means that what's on the left and what's on the right, at that stage of the algorithm, they were closest to each other. So they were grouped together. The height vertically of the connector lines, these heights, notice how down close to the bottom, the heights are kind of small. They're certainly small relative to these heights at the later stages of the joining process. The heights of the little join points are actually distances. They're the distances from the behind-the-scenes calculation. In the early stages, there's lots of individuals who are close to each other. So you have lots of short distances between things that are being joined together. What you're looking for in a picture like this is where does there begin to be a big jump in distances between groups. You're trying to find groups, individuals in this case, that are more similar to each other than they are to others. And an indicator that you found one will be that the distance between the groups that you discovered are big. Like it's hard to put these two groups together because they're so different. So we're looking at a picture like this, it's called a dendrogram, for places where there's substantial jumps. Let's look at the very top, for example. The very top represents the final join point where all 1,016 players were put together into one big group. At that point, there were two groups. There was this collection over at the right, and then this big collection over on the left. That's where we were currently at that stage of the algorithm. And then the distance between those two big chunks is a function of this height right here. It's very big. There was a big distance between these and those. Based on that big distance, I feel comfortable saying I think we've discovered a clustering in the data. If nothing else, I'm confident in saying that these individuals are different from those individuals. If you go further down, we could consider at this point, this was the next, these guys were joined, and then it looks like there was a tie here. But you could keep going down and investigate each of these join points. So right here, for example, there was this collection joined with that collection, and the height was about like that. We need to decide how big do the heights need to be for us to say, I think we've discovered a real cluster. Down at the bottom, these groupings together, the clusterings way at the bottom, we don't look at those as anything substantial or informative. We look at that as just noisy similarities among individuals. We're trying to find the big, substantial groupings. So I'll leave it at, well, no, we got time. Never mind. So we're looking for that type of thing. In a picture like this, I'll show you some specific tools for doing this. But in a picture like this, we would probably end up thinking, here's a cluster, there's another cluster, and there's a third cluster. We're going to do hierarchical clustering. We're going to look at a dendrogram, and we'll look at one more picture that'll help us decide how many clusters does this suggest. Suppose we said, I think there's 3 clusters in this data set. There's the over at the left and kind of in the middle and then over at the far right. I think there's 3 clusters. Then the next stage is to characterize those clusters. What is it about each grouping that makes them unique and distinct from the other groups? Kind of like when we did principal components, we discovered these principal components, and then we wanted to know what characterizes the principal components. What's kind of the story behind them? In this case, each individual, we have 6 variables. So we could, for example, compute the average of those 6 variables in this group and compute it for that group and for that group. And if you compared those vectors of averages, that would tell you some pretty quick information. Like one cluster tends to be all the Hall of Fame players, and another cluster tends to be all the players who only played one season, and so on. Okay, so how about we go to the whiteboard real quickly here, and I'll just fill in the last portion of this slide. The hierarchical algorithm is what I just described and illustrated. It gives rise to a dendrogram, and we have to decide what we mean by linkage. The other major clustering technique that we'll see is called k-means. And I think I will show you k-means after we look at the hierarchical clustering details a little bit. But k-means is a very simple algorithm also. It's just a different way of approaching the problem of trying to group. They're different though, and they'll probably result in slightly different pictures. If you do hierarchical clustering, you find 3 clusters, and here's their characteristics. If you do k-means clustering and ask for 3 clusters, they won't be exactly the same. There'll be some differences. So again, what you would ideally do is maybe hierarchical and k-means clustering, and try to report as sincerely as possible a consensus. Seems to be between 3 and 4 clusters, and they tend to be of such and such characteristics. So before we go back to the notes, let's stay here for just a second and investigate a bit further. The hclust function, I saved the output to this object called hcout. If you look at the help file, for example, remember that part of what they tell you, there's a section called value of every help file, and that is what you get back whenever you call the function. So my hcout object has some information in it. Let's look at a couple of these. hcout $merge. You know what I think will be even more informative is if we change TAC, and instead of looking at individuals, because there's so many of them, it's hard to see, let's look at the variables with these data. Again, I'm just deciding, do I want to group the individuals together, or do I want to group the variables together? As an illustration, let's group the variables. Here's the new picture. That's not what I expected. There it is. So it looks a lot cleaner because we only had 6 things to put together. The first, or which of the 2 variables were closest to each other? If you took the vector of the column that was a particular variable and computed a distance, a Euclidean distance between that column and one of the other columns, which 2 columns were closest to each other out of all pairs? it would be these two, because they were the first ones to be put together. The hierarchical clustering algorithm would start with a 6x6 distance matrix. So each off-diagonal element is a distance between one variable and another one. And the algorithm begins by putting together the two individuals who are closest to each other. This height, over at the left vertical axis, there's a label of height. If you carry the height of this horizontal connector here over, that is the distance between those two variables. So let's just verify that. The distances, let's print them out. Distances, okay. So these are the distances between our 6 variables. Hierarchical clustering is going to look through here, who is smallest? Where's the smallest distance? And it appears to be right there. Am I right? I think so. Yeah. So step 1 in the clustering algorithm is to put those two variables together, at which point there's now 5 clusters. Hits, RBIs, home runs, slugging percentage, those are all individual entities still. But now there's this new group of average and on-base percentage. I'll have to show you later how to proceed with updating the distance matrix, because I need to lecture on what the linkages are. But step 2 would be to group or recompute a distance matrix where one of the elements is now the on-base percentage and average variables together. But it's then the same routine. Look through that revised distance matrix, find the smallest number, group those together. Recompute the distances, find the smallest number, and so on. So this 2,227, if we could see with enough clarity, equals the y-axis value over here. The distance between average and on-base percentage was that 2,000 something. After recomputing the distance matrix, the closest pairing was between slugging percentage and the new cluster we created. So in step 2, slugging percentage was lumped in with these two, at which point there's now 4 clusters. Hits, RBIs, home runs are still their own thing, and now there's this group of 3. Recompute the distances, and ended up with home runs being added in. Do it again, ended up with RBIs being added in, and then finally hits. Okay. Now let me go back to doing the clustering on the individuals briefly. The picture was much more messy because there's so many individuals. But I do want to show you something additional. In the help file, one of the things that we get out, I should have showed it with you. I should have shown it a second ago. Let me, go back to what we had. Distances of the variables. Okay, hclust. And one of the elements in this object is called merge. And you'll get a little bit of practice with playing with this, but what merge represents is the history of how things were joined together. Think of hierarchical clustering as an iterative algorithm. It's going to run p times, where p is the number of individuals. It's going to group into pair, then do it again, pair, 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 until there's only one big group. So the first row is the record of the first move. And this -4, -6 syntax means that variable 4, the individual variable 4, and the individual variable 6 were put together. -4 and -6 indicate these were the original items in element 4 and 6. Step 1 was to put them together. Step 2, remember, was put slugging percentage into that new group of 2. So now it's a group of 3. So the second row is get the 5th original variable, which was slugging percentage. Go get the 5th original variable, that's the -5, and put it together with what you defined in step 1. That 1 does not have a minus sign. So this second row means put together the 5th individual variable with the cluster defined at step 1. Similarly, this one says put the second individual variable into the group that you just created in step 2, and so on. So if you use hierarchical clustering, you'll get practice with making the dendrogram. You'll get practice making another picture that'll help you decide in a principled way how many clusters are there. And then you can go through the details if you want to investigate just exactly who went with who at what step. And associated with each of those merge events, you also have the distances recorded. So these are the heights. In the picture, the dendrogram picture, these are called the heights. So HC out $height says that that first merge event, putting in variable 4 with variable 6, the distance for that merge event was that 2,227 that we saw. The distance between variable 5 and the grouping of 4 and 6 is 4,456, and so on. Just real quick while we're right here, the picture that I've referred to a couple of times for helping you decide how many clusters there are is super easy to make if you just plot the merge heights. So if I say plot a vector, it's just going to go plot the values of my vector on the y-axis, like this. So the first distance was 2,200, the second distance was 4,500, and so on. If I connect the dots, we can interpret a picture like this like a scree plot, like we did with PCA. With principal components, we made a picture that showed proportion of variance explained as a function of number of principal components. And we said, pick the number of principal components beyond which it's flat. Same strategy applies with clustering. If you look at the picture of the merge heights, you're looking for jumps, substantial jumps. When there's a big jump in combining two groups of entities, that represents a substantial structural component that you've found. So you want to keep differences that are high distance differences. So in a picture like this, a scree plot with clustering, let me draw one. Let's just do index height. In practice, what you're looking for ideally when you do hierarchical clustering and you're trying to decide how many clusters should I say that there are, is in this picture of the merge heights, an elbow, looking for an elbow where there's big contribution from separating there. There's a lot of info separation there, a lot of separation there. And beyond, every other join that happened beyond that seemed to be minuscule, relatively. So in this picture, let me just address this because it's been a point of confusion before. This would be the final merge event. That dot, whatever that height is the distance between the final two giant clusters that are put together. If I saw a picture like that, and that's the last one right there, this is the next one, then I would say I think there is one real difference. I like that green point because it's substantially bigger than the others. So I'm going to say one of my merge events was like substantial representing structure. That would mean two clusters that I've discovered. If I have the picture on the right, I see that the last merge event is by far the most informative. Everything else is flat, relatively speaking. If that's the case, I've discovered two clusters. Whatever I put together at the very end was what was so different from each other. So let me just write that. This would be two clusters. Over on the left, I would include all these joins where there's a substantial jump. So I would include and then you just have to think about what are we saying about how many clusters. So if I pick just the last one, that's two clusters, 2, 3, 4. Based on the picture on the left, I would say the last 3 merge events represent real structure that I've discovered. And that means I've discovered 4 clusters. In your homeworks and probably on your exam, you'll do clustering, you'll see a scree plot, and I'll ask you how many clusters would you say there are. So you interpret a picture like the way I just described. And then the next question would be, what characterizes, suppose the answer is 4. I think there's 4 clusters based on this picture. Then the next answer would be, what characterizes those 4 clusters? So you could go look at the averages of the variables in each of the clusters, for example. You might look at the variances. You could look at different ways of comparing the different clusters. But that's what clustering is. You discover groups, and then you try to diagnose what is it about these groups that make them groups. All right, so let's see. Next time, we'll keep talking about hierarchical clustering, show you another example, and then I'll show you k-means clustering. And then next week, we will circle back to the correspondence analysis, which is like the PCA for categorical variables. And I'll also show you another kind of specialized technique for numeric variables called canonical correlation. And very briefly, I'll show you something called multidimensional scaling. These are all just different ways of, for different types of data, doing this dimension reduction trick, discovering component structure in a data set. Okay, thank you.